indefensible, really. Should we play alto? Really great game. Okay, so it has a Zen mode, very important, where you just play forever. Zen mode. Yeah, you're a snowboarder. You should dig this. The original one is snowboarding, where you catch llamas, because, right? Yeah. Okay. Okay, so this is interesting. So let's try to figure out the size of the largest component. So we haven't done this, right? We haven't done this, right? We did an evil thing, right? We did that funny little calculation which gave us the right answer for Poisson degree distributions, but was wrong. The little delta equals sum of pk delta to the k. So we're going to have to figure out how to do this well. I'm going to show you eventually that there's a beautiful way to do this without generating functions. But this is all good, very good. Okay, so now we're going to introduce. So we've had. So there's still things are going to be connected. We had a big P sub k, right? Have I written that down? I guess. Yeah. Okay. No, it's coming. We had a big P sub k and a big R sub k, right? And they were about degree distributions. The degree of a node that you choose randomly, or the number of other friends that a randomly accessed node along one edge has, right? So those two are connected. There was a Q in the middle, but we forgot about that one. Okay, so now we're going to have these two pieces. There's going to be a pi n and a rho n. And so these match up in that this is P and this is R, right? In the Greek thing. So that's purposeful, right? So this is going to be connected to the P1, P sub k, and this is going to be connected to R sub k. And so we can see that in their definitions. So we're going to randomly choose a node, and it belongs to this belongs to a finite component of size n. That's a bit of a tricky piece here. It's the finite component. So it could be in a giant component. Problem is with a giant component is infinite, right? There's an infinite number of elements in there. So we need kind of pi sub infinity. The way this is going to work is if there's a giant component present, this thing is just not going to count it up. It's just not going to be there, right? So the sum over all of these pieces will be the probability that a node that you've chosen is in a finite component, right? So you'd think it should be that the sum over these probabilities should be 1. It's just the probability that a node is a part of a component of size. Well, it can't be of size 0, but just say it 1, 2, 3, 4. We just don't. It doesn't work out. So we just don't count the infinity part. It blows up. So we will now have a case where the sum of this thing will be less than 1 potentially, and then 1 minus that sum will be the size of a giant component. Excitingly. Okay. Similar sort of story here. This is going to be the one that everything revolves around, and this is probably that we're going to run along an edge. Well, so we run along an edge. There's a probability that when we hit this node, randomly accessed node, that it leads to a finite component of size n. And I'll have some pictures to try and explain this to you and to myself. Certainly takes a little, you have to think about this, and when you look through papers and so on, it can be a little messy. Okay, so again, there's this connection between these two. This is just about neighbors. It's a local thing, and this is non-local, and it's about component sizes. So you can see this is a bit of a trickier thing to think about. Okay. We shall pile on, and let's see if we can do it. It's very nice. It's quite beautiful.